we're covering the 2 sections in chapter 11. And then we're all going to go off and eat too much and have too much fun over the weekend. But then we're going to come back fresh and ready to go. Because on Monday, we're doing the last section of the whole course, 12.1. I'm telling you, it'll take us a half hour at tops to do 12.1. And then we're going to spend the rest of Monday reviewing for the exam. And then the exam is a week from today on chapters 10 through 12. 10 is what we just did. Today we're doing 11 and the one section of chapter 12 next time. Life is flying by. And then the very next time I see you is when you're doing your project presentations. If you weren't here last time, see me at the break to get the handouts for the project. Make sure you have the directions. Essentially, you're taking your old project and adding 4 new things to it and fixing anything if you need to. Correct? Questions about my little agenda there? We have another day after that where we might do more project presentations if we didn't finish. If not, we're just going to review for the final that day. So usually the second day is finish the projects and do a review based on whether or not we got them all done. Depends on how many groups we have. No questions? We're good? All right. So I'm on page 152. Page 152, goodness of fit. It only goes up to 163. We're almost there. Almost there. All right, so goodness of fit is yet another hypothesis test that tests when you have a categorical variable with lots of categories. So for example, let's say I ask everybody what your favorite colors are, and some of you say blue, and some of you say green and purple, and I might ask you to test the claim that all the colors are equally likely to be chosen. So I have lots of different categories, and I'm asking if maybe they're all the same. That would be a goodness of fit claim. How well does the data fit what I just claimed in terms of all the categories are equal with my claim? There might be slightly different claims, but it's usually when you have multiple categories, are they what we think they are? You're really testing proportions in disguise. If I was doing my color example, it might be, say there were only 5 colors chosen, that maybe each color would be 20%. 20% blue, 20% green, 20% purple, red, and black, or whatever they were. So that would be actually a percentage problem, but it doesn't really show up in the calculations. But sometimes in the wording you'll hear about the proportions are the same across the categories. That's really what we're testing for. So we use a chi-squared goodness of fit test. Half of you, roughly, already have this in your calculator as the chi-squared GOF test, goodness of fit test. So do me a favor, open up your calculator, stat, tests. Not all of you will have it, don't worry, there's a fix for that. There's a chi-squared, and then there's a chi-squared GOF. Everyone see where we're looking? Who has the chi-squared GOF? Ooh, a little bit more than half. Who doesn't? 1, 2, 3, 4. Okay, so the 4 of you who don't have it, there's 2 options for you. There is a program that you can download onto your calculator in the Math Lab. We have them on all of ours, and we can transfer it to you in less than a minute. It's called GoodFit 83. If you don't have it on your calculator, or you can do it by hand, which is actually how I'm going to demonstrate it today. I don't have it on my calculator either. And doing it by hand isn't a whole lot of work. It could be. But those of you with the calculator function can check my work for me as we go through, because you'll be done well before I am. So I'm going to demonstrate it by hand, but you can also do the chi-squared GOF if you have it, or the GoodFit 83, which we can download for you. All right. Let's look at my first example. Well, before the example, let's talk about the formula. There's this chi-squared formula. Chi-squared equals this mess here. Looks like this. K minus 1 degrees of freedom. What has degrees of freedom been before this? N minus 1, where N was your sample size. So K in this case is how many categories you have. So when I gave my example of 5 different colors, K would have been 5. even though I may have asked 40 of you the question, my sample size was 40, but K would have been 5. So I would have had 5 minus 1, I would have had 4 degrees of freedom. So there's degrees of freedom to go with your chi-squared. And then there's this weird looking stuff here. What does this symbol mean? Sum. We're going to be add a bunch of things up. So for each category, we're going to be adding something. And then there's these O's and these E's. We're going to talk about those as we go through the examples. O are your observed numbers, the numbers you actually counted in your calculation. So if I had asked you all to choose your favorite color, I would have said this many people chose blue and this many people chose green. Those would have been what I observed. Really, I would have heard it, but I would have observed that. Expected would have been what you're expecting it based on the claim. I expected them to all be equal. We're going to go through that, and then we're going to go through the whole formula. Okay, so example 1 has this information here, and they're always having these conversations lately about getting rid of the penny, because no one really uses pennies anymore, and they're not worth much anymore. Not like the old days when I used to scrounge them up and go walk to the store to buy candy with them. I only needed 4. No, 5 sometimes, 5 sometimes. So they're talking about getting rid of pennies, and they're looking at checks. When people write checks, which they don't do much anymore either. When you write a check, some people don't write out the cents portion of the check. My mother-in-law is a perfect example of this. If you tell, she goes to the grocery store, she still writes checks. They tell her, you know, that her total bill is $20.83. She'll just write it for $21. She doesn't want to write out the 20. She just rounds up and gives them a whole number of dollars. So the question is, they're checking to see if a lot of people do this. A lot of people ignore the cents portions in their checks. So this table here has the 4 different categories. So someone took a whole bunch of checks, and they looked at the last, I'll write it over here so I can subtract them. They looked at the last digits, like how many checks had 0 to 24 cents. So, you know, if your check was, for example, $18.12, that would have been in that category, how many cents there were. And then how many were in 25 to 49, and how many were in 50 to 74, and 75 to 99. So these are the 4 different categories. That could be on a check, right? If you write a check, it has to be in one of those 4 categories. Pull that door closed, please. Thank you. And then what they have underneath there is just the number of checks that they counted. So somebody looked at a bunch of checks and just counted how many of them have this much in the cents portion, how many have that, and so forth. So somebody went by and counted and got these numbers: 61, 17, 10, and 12. These are the observed values. Observed values. Someone observed how many were in each category. Just making sure we understand what we have there. So you look at a check, oh, this one has 53 cents. 53 cents, it got counted over here. This one has 72 cents, so I'll count it in there again. Based on a quick glance at the data, what does it look like? If you were to describe what happened with these checks on a quick glance.
A lot of people write off 24 cents an hour.
Yeah, a lot of times it's 24 cents and below, which means maybe a lot of people are like my mother-in-law and they just round to the nearest dollar, which would be 0 cents, right? That's maybe what they're checking for, to see if there's a lot of them that get rounded to 0 cents. Seems like maybe that could be the case based on this. So if you look at what it says up above here, it says use a 0.05 significance level. Example 1, nice if I labeled it. Use a 0.05 significance level to test the claim that the 4 categories are equally likely. So they don't look equal. They look different from equal, but the question is, are they different enough? Because even if they're equally likely, they may not come out exactly the same, right? But they could be close. So are they equally likely? So I wonder how I'm going to write that. What does it mean? This P for probability or for proportions. That's what I was saying, that it's kind of a hidden proportion problem. We're saying that the proportion of checks in each category should be the same. How many categories do I have? 4. So I'm saying that the proportion in the first category is equal to the proportion in the second category, is equal to the third, is equal to the fourth. The proportion in each one would be the same, that's the claim. I couldn't hear you.
Who's right now?
I mean, you have to write down what your H0 is, that's our H0. Every time we do a hypothesis test, we still have to do our 5 steps. Everyone okay that that's our claim? What do you think we write for H1?
This is not
Not
equal.
equals.
Yeah, we can't write not equals. Because, don't copy this down. I'm assuming that what you meant was this. Do not copy this down, because I'm about to erase it. I'm assuming that you meant this.
Yeah.
This is not the complement of that. Let me tell you what. Don't copy it down. If anybody copy it down, I'm going to come over here and smack you. Okay, maybe I will. I'm not very strong anyhow, don't worry about it. Let's say I claim that you're all the same age. All of you. You all have the same age. If I'm wrong, how are you going to prove me wrong? Do you have to show me that everybody has a different age from everybody else?
No.
Just one has to be different, right? So if all of you are 20, I only have to find one person who's not 20, and then I'm wrong. I don't have to show that every single person has a different age than the person next to them. That's what this says. This says that every proportion is not equal to all the other ones. So we can't actually write out a nice, simple claim for H1. What we write is exactly what Kirsty just said, at least one is different. That's all we can really say. At least one of those proportions is different. So if I claim that all of you are 20, I just have to find one person who's not 20, and then that's the complement. Okay there? So the HO and the H1 are a little bit different here. Okay, so we did that. I want to now talk about these expected values, the E's. My first question for you is how many people were in this survey, or how many checks, sorry they were checks. How many checks were in this survey? 100? How do we know it's 100? Did it tell you it was 100? They told us there were 100? Oh, and then someone else said add them up. So if they hadn't told us there were 100, do you agree that we could have added these all up to see how many total checks there were? If we add 67 plus 10, all this, the total, n equals 100 checks? Do they add up to 100? I'm double check. Okay, I'm trusting you.
Yeah.
Okay. So if they hadn't told us, we could do that. Now, I'm going to move my output down a little bit to my way. Just a little bit. Underneath these expected values, underneath these observed values, I want to write the expected values. The expected values come from the H0. The claim is that they're all the same. If I have 100 checks and the same number is in each one of these, how many goes in each one? 25. How'd you get that? He took 100 and divided it by 4. He took the 100 and divided it equally into 4 spaces. 100 divided by 4 would be 25 in each. Does that make sense? If they really were equally likely, I would have had 25 in each one. I'm going to write those in here. 25, 25, 25, and 25. So these are the observed, these are the expecteds. Maybe even give it another little row, right? So every time you're doing the goodness of fit test, even if you have the calculator, you have to come up with the expected values, which come from your H0 claim. Questions there? So from here, those of you that have this on your calculator, you can open it up and start working. It'll ask you for your expected values, it'll ask you for your observed values, and you're going to be already done before I even get going on the next part. For the rest of us though, I'm going to actually use the formula. I have to do exactly this. I have to add up all the O's minus the E's squared divided by the E's. So watch me write this out carefully. In my first category, you got the clicking, people who have the nice calculators are all like ignoring me, I like it. The O minus the E, 61 minus 25, squared, divided by the E. See what I'm doing there? Divided by E, which was 25. Plus, same thing for each one, 17 minus 25 squared divided by 25. Plus 10 minus 25 squared divided by 25. That's doing this formula. For those of you who don't have the nice shortcut, it wouldn't kill you to type that into your calculator. The rest of you are like, I'm not doing it. But we agree we can handle that? If I did all of this calculation, those of you that do the calculator are going to tell me what it comes out to be. What did it come out to be? You guys already run the test, the chi-squared GOF? What'd you get for your chi-squared?
70.16.
70.16? I see some nods. So let me pause for a moment. I got that from the people who had the calculator. The people who don't have a calculator, let's say I'm stranded on a desert island and I really want to do this problem. You never know what's going to happen. I'll have to keep myself entertained when I'm on that island. I could work this out in the sand with a stick. It'd take me a little while. But I could subtract and I could square and I could do all this work and add these all up and I would get the same answer. So the calculator just did all this for us, but that's exactly what the calculator just did. So if you wanted to, for fun, over Thanksgiving, work this out, you would get 70.16. What do you think this is in terms of our test? What do we call it? That would be the test statistic. The test statistic. Remember, we've had lots of different test statistics. Sometimes they're Z's, sometimes they're T's, sometimes they're F's, sometimes they're chi-squareds.
I had a question about that really quick.
Yes.
Regarding last night's homework online. I thought the R was, it's not the test statistic, right?
Well, this is interesting that she asked that. She's asking about the correlation questions online. Technically, the R is the test statistic, but I noticed was I was helping someone in the lab yesterday
Yeah.
that the my stat lab wants the T to be the test statistic. Yes. Usually we want it to be R because we're looking to see what the correlation is, but my stat lab did want T to be the test statistic.
Okay.
And I didn't catch that till I was helping somebody either.
Yeah, no, I thought it wasn't relevant for this kind of work.
Yeah, technically it's not, which is why we don't ask for it, but it is, came out of a T test that it really was doing. Little side note. So everyone okay with this? So you know we have our 5-step process. Step 1 is to write your claims. Step 2 is to get your test statistic. What's step 3? P-value or critical values. I'm going to do both. I'm going to do the critical value first. Then those of you who have the p-value, because those of us who don't have that calculator could still do this without the p-value. Okay? Remember chi-squared looks like this. Starts at 0 and goes up only. This is the chi-squared distribution. Notice what it says right up above this problem about the tails. You see that?
Always right.
Always right-tailed. Every time you do a goodness of fit, it's a right-tailed test only. So we're looking for the area in this little tail to be what?
The critical value.
The significance level. But we're going to get the critical value to cut that off. So the 0.05 was our significance level. So this area in here is 0.05. 0.05. And the question is, what is this chi-squared star right there that cuts off that area? How am I going to find that? On our table. Which table? There are lots of tables.
Critical value Pearson correlation coefficient?
Ah, are we doing correlation?
Nope.
Nope, so we can't look there. But at least we can know how to read that and do process of elimination.
So we do the
I don't know if you
chart
guys,
T1, huh?
yeah, exactly. So I don't know if you heard Kevin, first he goes the correlation coefficient, and we're like, no, wait, we're not doing correlation. So he caught it. He said that, he called it the chi-square, but I call it the chi-squared. It has the little chi-squared on top, page 7.
So degrees of freedom.
Yeah, remember degrees of freedom we mentioned earlier? It's k minus 1 degrees of freedom, and what did I say k was? The number of categories, not your sample size. My sample size is 100, but my categories in this case is 4. So what's my degrees of freedom? 3. My degrees of freedom,
It's 0.05.
4 minus 1 is 3. And we're looking at 0.05. Is the area to the right? Looking on the right one here, going down to the 3, and what do you see there? She sees 7.815? Do we see that on the table? You're shaking your head, Jenna? No, you're good? Okay. Anybody need me to point at their table for them? 7.815. When you do these online, they will ask for critical values sometimes and p-values sometimes. So you want to make sure, yes.
Since right there, the degrees of freedom was 3, does that mean we have to put it as 3 in the calculator too?
You don't,
99.
oh, when you did the chi-squared GOF, you would have had to put that in as 3 as well.
Oh, yeah. Well, then,
I put in
99
100.
is, we
Did it ask for n or did it ask for degrees of freedom?
It asked for degrees of freedom.
Yeah.
Ah, so degrees of freedom, it probably won't change this, but it'll change your p-value. Who put in 3 and who put in 100 for their, so when you ran the GOF test, which I didn't show you how to do because I don't have that in front of me either, they're telling me it asked for degrees of freedom,
Yeah.
we should have put in 3. Did some people put in 3? And some people put in 99, some people put in 100? But everyone agreed that it should have, what'd you say?
P-value's way down.
The p-value will change, but you should have had the same test statistics, that's just the same calculation here. We all get 3 now is our degrees of freedom? I'm glad you asked that, Amy. Okay, so this is my critical value. This chi-squared is 7.815. What do I do with that critical value?
You see if the test statistic falls in the critical, the cutoff before or after, and it's going to determine whether you reject it.
Great, I check to see, if I can speak, I check to see if my test statistic falls in the critical region, the shaded region, which I like to call the rejection region. If it's in there, then I will reject H0. So this started at 0, this is 7.8.
Obviously.
70.16 is way the heck out here, off the end of my board probably. I'm gonna mark it over here just because I'm gonna not have enough room, but do you agree that 70.16 is definitely to the right of that somewhere? So right there, that's enough information to tell me to do what? Reject H0, that's my step 4. Reject H0. Because I'm in the rejection region, the critical region. Those of you who had the calculator, did you find the p-value? I can't find this without the calculator either, so I'm just trusting you guys. It just says 0?
It's negative, way negative.
Well, it can't be negative.
I mean, you know.
Oh, it has a negative exponent.
At the end.
Yeah, it should be really tiny,
Uh-huh.
which rounds to 0 plus. Based on my picture, why is it really tiny? Yeah, because you said it's all the way over there. If 70 was, if I really was counting, say, by 7s, 70 would be way the heck off the end of this board over here. And that little sliver to the right of it would be so tiny you can't even see it. It rounds to 0. The tiniest little sliver. Remember your p-value, yes ma'am?
What's the red number?
70.16. It's the same as my test statistic. I was just checking to see where it is in that picture. Thank you. I'm sorry you're all on the other side of the room. It is kind of a sloppy 1.6, I'll give you that. So both the p-value, which is definitely less than 0.05, and the critical value tell me to reject H0.
What's p-value? What was that again? Or
P-value is the probability of your results. So our results, let me back up, add a preface to that. If this claim is really true, if they are equally likely, the probability of getting these kind of results is almost impossible. So, which is why we're rejecting the claim that they're equally likely. So the p-value represents the likelihood of getting your results if H0 is true. Because we know that sometimes you could be off from exactly the same, a little bit, but then we're saying it's really, really unlikely to be that different if they really are equally likely. What's my last step here? The
Conclusion.
conclusion. What do I say? Go back and see what the original claim was.
It's not enough evidence to,
There is
There is
sufficient
sufficient
evidence
evidence
to
for
support.
rejection on that one.
Okay, so you guys started off the same, but then you didn't all agree. There is sufficient evidence, let's stop right there for a moment. Why is there sufficient evidence?
Because we rejected.
Because we rejected. Remember, I keep saying, if you're convicting somebody, it's because you had sufficient evidence. If you're rejecting, it's because you had sufficient evidence. There is sufficient evidence
To warrant rejection.
to warrant rejection or to reject the claim, because our claim was H0, and we just rejected it. So we can't say we're supporting or not supporting it, we're only rejecting this claim. So there is sufficient evidence to reject the claim or warrant rejection of claim that the 4 categories are equally likely. Okay there? There's a follow-up question. The author expected that many checks for whole dollar amounts would result in a disproportionately high frequency for the first category. Do the results support that expectation? Why yes, Evan?
Because we rejected the original.
Yeah, we rejected H0, which means they're not all equal.
Right.
So we already have evidence that they're not all equal, and then now, when you look at the data, this one looks a lot bigger than all the other ones. If we had failed to reject, and that still looked bigger, the answer would have been no. It just looks bigger, it's just not different enough. But because we rejected, we now know they're not all equal. Questions on those? Good? Okay. Ready to try another one? That was one whole page. Okay, let's do example 2. Now we're going to the horse races. They have the frequency of wins for different post positions in the Kentucky Derby horse race. I don't know if you're all familiar with horse races. I've never been myself, but I've seen them on TV. Here's my fabulous artwork. So there's this track that the horses run around. Right, they all run around the track. This is the inside and the outside, right? But when they start, they kind of line up the horses over here. Right, the horses are all lined up, and then they start running. They open the gates and they all go. This is my fabulous artwork that shows the horse race. The claim is that this guy right here, this horse right here, since he just needs to kind of run straight, he has an advantage to this guy, which is going to start running and have to go like this, right, to get over there, because the inside is the shortest distance. So the claim is that this guy has an advantage to this guy because he has to run faster to get into the inside like everybody else. So as you go around it. So that's what they're talking about here. So the post position at number 1, this is number 1 up here, is closer to the inside rails, so he has a shorter distance to run. And so the question is, does that affect the likelihood of winning? If you're going to go to the horse races and bet on who's going to win, Does where they start make a difference? It looks like it does, especially if you draw like I do. Looks like it does. So it says use a .05 significance level to test the claim that the likelihood of winning is the same for the different positions. I want to leave that up there for now. I'll put it over here. This is example 2. I want to silence here. What do I write for the claim?
You do the whole P1 equals P2 equals P3.
Yeah, P1 equals P2 equals P3.
All the way to P10.
All the way up to 10, but I'll show you a little shorthand for not writing them all out. But it is saying that all 10 are equally likely. So we say P1 equals P2 equals P3 equals ... equals P10. That pretty much implies that all 10 of them are equal. Put some little dots in there. That's the claim, that they're all equally likely? So what do I write for each one?
At least one is different.
Say that again?
At least one is different.
At least one is different? Same reasoning as before? At least one is different? I'm going to recreate my data here real quick so I can point at it. I'm not going to write out the whole thing by hand, but I will start. So this list, 2, 3, 4, 5, 6, 7, 8, 9, 10, good. This list represents what?
You observe.
The observed values, right? The different numbers that fell into each category. What'd you say, Jenna?
First of all,
Yeah, how many times a horse won in this position, how many times a horse won in that position, and so forth. But these are the observed. These are the observed. So 19 times the horse that was in number 1 position won the race, and 7 times the horse that was in position number 6 won the race, and so forth. So that's what they're doing. They're counting how many times the horse in each position won the race. What do I need next to do this problem?
it's the E.
I need the expected values. What'd you say?
I said the E.
The E, the expected values? How am I gonna get them? Add these all up. I need to know how many total wins I'm talking about here, right? I have to have my total. The last example I gave you, N, I don't think they told us how many horses are in here. So I have to find N equals the total number of wins.
It's 114.
She says it's 114? Yeah, some agreeing? If we add all these up, there's 114. What do I do with that 114?
Divided by 10.
Divided by 10, because I'm saying all of those 10 should be equally likely. So my expected values in this case should be the 114 divided by 10, which is 11.4. Now technically I know you can't have 11.4 wins in any category, but if they were all equally likely, it would have rounded to 11.4. So it's okay to put 11.4 in here for every single expected value. Sorry, what did I hear?
I was just asking it for each one.
Yeah, each one. So I'm writing it 10 times. So we expected slightly more than 11. In a sense, you're expecting 11 or 12 every time in each one to make them all close to equally likely, because you can't get exactly 11.4. You have to find your expected values. Those of you who have this calculator function are going to now do this calculator function. You're going to put in your observed, your expected. What are you going to put for your degrees of freedom?
9.
9. Why 9?
K minus 1.
There's 10 categories. It's K minus 1. So we know the degrees of freedom is the number of categories minus 1. So you're going to put in 9 for your degrees of freedom. The rest of us who don't have that calculator are actually going to write out 19 minus 11.4 squared divided by 11.4. Plus, I'm not going to write them all because I will run out of ink and time before I get them all written. And I have to do that for all of these till I get to the very last one. 11 minus 11.4 squared over 11.4. That would take me a while because I have 10 different fractions to add up. But the rest of you are just typing those into your calculators. There's a handful of you, I think there were 4 of you. Come stop by the math lab today, get that into your calculator. It'll do the same thing where it just asks for the observed and the expected. It'll make your life easier. What do we get for that?
13.19.
13.19? I see some nods. What is that 13.19?
The test statistic.
That's my chi-squared test statistic. That's my test statistic. So I've done step 1 was to write the claims. All of that was step 2 to get the test statistic. Bring my picture over here for steps 3 and 4. Erasing my horse tractor. Step 3 is either critical values or p-values. I'm going to do both. So when I draw the picture, was it 0.01? Did I write it down? I didn't. 0.05. Alpha equals 0.05, significance level. Always a right-hand tail test. This is 0.05. Degrees of freedom is 9. What is the chi-squared right here?
13.9.
13.9?
You
I'm not
want
looking
critical
at my
value or
chart.
chi-square?
What did I say?
Chi-square,
Okay, so what is the chi-squared critical value?
16.919.
16?
Yeah.
Point, I don't have it open. What'd you say?
919.
16.919? I don't know what this looks like. It doesn't look at chi-squared with a star, though. Chi-squared with a star is 16.919. Is that what I heard? Where'd they get that? Jesus, holds this up. On the chi-squared table, look at under 0.05 and degrees of freedom 9. So this is my critical value, 16.919. What do I do with that?
Tells you whether to reject it or not.
Tells you whether to reject or not. We're going to take our test statistic, this 13.19, and see where it falls over here. If this is 0, and this is 16.9, where is my 13.19? On the left of that, right? Somewhere over here, maybe?
Failed to reject.
13 point, is it 19? 13.19 is right here. So it's not in the critical region, not in the rejection region.
Failed.
So it's failed to reject H0. That'd be my step 4. What is the p-value? Those of you who have that calculator,
It's 0.154.
squeeze it right here. P-value. Tell it one more time.
154.
154. What do I do with the p-value?
Put it up against the alpha and see.
Compare it to the alpha, see if it's less than alpha. Definitely greater than alpha. And because my p-value is bigger than alpha, that also tells me to fail to reject H0. Notice that everything we did in chapters 8 and 9 just keeps coming back. Which is why we got to make sure we know when to reject, when to not reject. And how to write our conclusion. I'll write the conclusion up over here so we have enough room. My conclusion is a mystery.
There is not sufficient evidence to warrant rejection of the claim?
There is not sufficient evidence I can tell that already because we didn't reject, so we didn't have enough evidence. So you could all say there's not enough evidence. So there's not enough evidence to, and because my claim, oops, it's way over here. Because my claim was H0, I didn't have enough evidence to reject that claim. To reject the claim that, what was the claim? The likelihood of winning, is the same for the different positions. Now, let me pause for a moment. You all got that conclusion? Now, the quiz I just passed back was from chapter 9, actually, but a few of you had trouble with the follow-up question. And I have to point out that just because you can write the claim doesn't tell me that you understand what it means, which is why I quite often ask the follow-up question. But you can write it, you know what the words are. But then the follow-up question is, should bettors consider the post position in the Kentucky Derby? So if I'm going to go bet on a horse to win, should I choose number 1 because he's more likely to win?
Yeah.
Yeah?
There's not enough evidence to reject it, which means it could definitely be true.
What could be true?
That they're all equal.
That they're all equal.
So it doesn't matter.
So she says, never mind. I'm glad that as you said it, you caught it. So first she was saying, yes, they should consider it. But then she caught it because she says, we didn't reject the claim that they're all equally likely.
So it doesn't matter.
So it doesn't matter which position you're in because we don't have any evidence that it makes any difference. They could all be the same as far as we know. We don't have any evidence that any one of them is more likely than the others. Not a single one of them is different enough to say we should consider that when we make a bet. We okay with that conclusion, that follow-up?
Because you're
Here's
saying
what
they're
my-
not all equal.
Do it again?
Because you're saying they're not all equal positions.
Well, our conclusion was that it appears that they are, right? So the answer is no, all positions,
Yeah, that's what I meant.
oh, okay.
Yeah,
It sounded backwards to me, sorry.
yeah, I did say it backwards.
All positions appear to be equally likely.
What I meant was if you're betting, it doesn't matter what.
Oh,
position.
yes. Equally likely. That's about as strong as we can say. We can't say that they really are equal, but based on our test, it appears that they're all equal. We don't have any evidence that they're different. So just like I could look out right now and say, you guys all appear to be the same age, because I can't find a single one of you who looks slightly older or younger. Doesn't mean you really are, but it appears that way because I didn't have any strong evidence. But that follow-up question is important. Just because you can copy down the claim isn't enough. You need to tell me you understand what it means. Okay, let's take a break for about 10 minutes. We've got one more example of this, and then we're going to move on to 11.2, which is even quicker and easier. I neglected to tell you one thing for those of you who don't have the great calculator and don't have this yet downloaded from the Math Lab. You can find the p-value using chi-squared CDF like we've done in the past. Remember chi-squared CDF? I'm actually going to do that again for example 2. Chi-squared CDF, you put in the left, the right, and the degrees of freedom. We've used that before. So if we were to check that, we could check our p-value from that last example. Our, where's my picture? Our test statistic was 13.19. If we wanted to find the area in the tail, remember it's always right tailed, using chi-squared CDF, what would I put in there?
13.19.
13.19,
We put 999.
9999, some big number. And the degrees of freedom for that last example was
9.
9. So we should get the same p-value that those of you who had the calculator function already got, which I can't remember what it was. Can someone tell me? Let's see.
0.154.
Say it again.
0.154.
So did you just calculate this as well? Did chi-squared CDF give us the same number? Is anyone punching this in? She's nodding, thank you. So you can get your p-value this way. So if you don't have the chi-squared GOF on your calculator already, if you can't make it to the math lab to have us download this one onto your calculator, you can still find the p-value by doing chi-squared CDF, always doing the right tail. Just in case the online problem's asking for both the p-value and the critical value. On an exam, of course, you could do it either way, just the critical value or just the p-value. I'll do this one again on the next example. Questions? Okay, let's do example 3. Example 3 is a high school biology class is doing an experiment with fruit flies. And they have the results listed below. And they were checking about the color of the eyes, red eyes, sepia eyes, and what kind of wings they are, which I'm not a biology person, so I don't know what a vestigial wing is. Who does? Anybody? What's up?
It's a wing that's left over from evolution.
A wing that's left over, like
So,
an extra wing?
Like if a dolphin had like a little like little bone sticking out from somewhere, it might be a vestigial wing. Like its ancestor might have had wings,
Huh.
but it evolved to not need it anymore.
So they have like normal wings and an extra one or something? Maybe?
It's like oh, I used to have like we used to have tails or something like
Uh-huh.
like, so we're gonna have like a
A
vestigial
little
tail.
leftover, okay. I
Yeah.
got it. So this is what I learned. I don't know any biology, right? So we're checking what color eyes these fruit flies have. They must have really good magnifying glasses, right, to look at their little eyes. What color eyes and what type of wings they have, whether they're normal or these vestigial wings. The heck you just gave us a lesson about, right? So they counted all these fruit flies and put them into their observed and how many of each they saw. The important thing here, though, is the claim is not that they're all equally likely. The claim is not that they're all equally likely. So let's read it again. So they're talking about these flies. There's the examples below, and it says, also listed are the expected proportions according to the principles of genetics. So this is how many should have been in each category. There should have been 56.25% of them that had the red eye with the normal wing. And there should have been 18.75 that had the sepia eye with the normal wing, and so forth. So you know, they're not saying that they should have all been the same. They should have all had these other percentages. See the subtle difference there compared to what we were doing? Let's talk about how to handle this test then. So we're still using a 0.05 significance level, but we're testing the claim that the observed frequencies agree with the proportions that are expected. What does that mean? I couldn't hear you. Were you thinking out loud? Are you talking to me or both?
So the 56.25
Mhm.
is the expected, what they expect, so then is that like a map, like a pair, the numbers paired?
It's like a pair that's paired up with the first category. Is that what you mean by a pair?
Yeah.
Yeah, so they're expecting the first category to be 56.25%. So we actually are gonna write that down. They expect the percentage for the first category, we're gonna turn it into a decimal, to be 0.5625. That's what they expect. That's the exact percentage for the first category. What's the expectation for the second category? 18.75. And notice that's the same for the third one. So we could save a little bit of space to say that P2 and P3 are both equal, but they have to be 0.81875. Well, we could put those two together because they happen to be the same. If they were all different, we would list them each separately. And The last one, P4, is 6.25%, which would be 0.0625. So I'll warn you right now, on the exam next week, there will be 2 goodness of fit problems on there. One of them will be like the ones we did earlier, where they're all equally likely is the claim. But there will be another one where they're claiming there's these different percentages. What happens is people do the beginning part of this section and assume that all the problems are the same, and they're not. So in this case, we're not saying that they're all equally likely. You okay there? How to write the claim? I think there's a problem on the lab, I think it's on the lab, maybe it's online, about M&Ms where the M&Ms company says that 8% are brown and 5% are blue and this percent are red. So then they're just giving you the percentage that they claim and you're gonna test to see if it fits what they're claiming. It's like you're doing lots of tests all at once in a way. What do I write for each one? At least one is different again. We don't know, they may not, maybe they're all close, but one of them's different. All we can say is at least one is different. Now here's where it gets tricky. Here's my observed. 59, 15, 2, and 4. I need to put my expected in here. This is the tricky part.
So 80 divided by 4?
I wouldn't write it in decimal form, hold that thought. I wouldn't write it in you mean like write this in decimal form? Expected is how many flies we expect. So imagine if I had thousands of flies, I wouldn't expect 0.56 of them to have those kind of wings.
So do you find the percentage of that from top?
We find a percentage of what? You're right, you're half the way there.
The total.
Percentage of the total. So we really are saying that 56% of the total will have this kind of wing and eye, and 18.75% of the total. Those percentages are of the total. Percentages of the total. So going back to what Kirsty just said, she wanted to take 80 divided by 4. Where'd you get the 80?
I added up the observed.
She added up all of these, the total is 80. Why can't we divide it by 4? What is that saying if we divide it by 4?
That means they're equal.
Ah, perfect. That means they're all equal, right? If they're all equal, I would divide it by 4. But that's not the claim this time, which is why I was telling you how this one's different than the other ones. If the claim was that they're all equal, of course, I would have 20 of each. But it's not the claim. Yes, Hector?
Would you divide it by the expected portion for each one?
I'm actually going to multiply, so I'm going to take 56.25% of 80. And I'm going to take 18.75% of 80 to figure out how many are in each category. So for each of these, I'm actually going to write it all in here. I have to take 56.25% of 80. All right, I'll simplify it here in a minute. But I need to know how many is that? What is 56.25% of 80?
45.
You guys just did it for me, you got 45? So I'm expecting 45 flies of my group to be in this category. I'm gonna just write it right underneath, you guys okay with that? This is just showing you where the numbers are coming from, these are the actual numbers.
And this is the E, right? This is gonna be-
Yes, these are the E's, these are the same E's here, expected. These are the expected, I just simplified it down below. So for number 2, I'm going to take 0.1875% of 80. Everyone clear why we're multiplying by 80?
This is the total.
That's the total. I'm rearranging it. So basically I'm saying I have these 80 flies. Let's rearrange the 80 of them to fit the claim. So I still have to work with those 80. Now what did you guys say that was? 15? So I know this one has to be 15 also, without even writing it down, right? Because the claim was that they both were the same.
Right.
So 45, 15, there's 15. And that last one over there, I need to find 0.0625 of 80.
It's fine.
I'm hearing 5. So these are my expected values. These numbers on this list.
Those numbers have to add up to 82.
Yes.
Yeah.
If you're thinking that you did your expected values correctly, the first thing you want to do is double check that your total here is the same as the total here. If it's not, then something's really wrong. Because the whole point is to take your 80 original flies and rearrange them. If they add up to something other than 80, you lost some of them somewhere, or maybe you threw some extras in. But if you add these all up, the total is still 80.
Observed and the total are both 80.
Yes. Because the observed and the expected are the same sample. One of them is just what you actually counted. The other one is how you would rearrange them to fit the claim. It'd be like if I said, I claim that every row has the same number of people. I'm observing that that's not true in here. But I could have some of you get up and move and then have the same in each row, and it's still the same number of people, right? To fit my claim. But always double check that your expected add up to your same total. Because a lot of people want to do what Evelyn's first thought was and just put the decimal in there, but it has to be a total number of flies. And if you put the decimals, it wouldn't have added up to 80. That's what makes this one slightly different. After that, it's now the same again though. Once we have our observed and our expected, we're going to go do the formula or the calculator, get our test statistic and so forth. So are there questions on the expecteds?
So the DF would be 79 then.
Well, wait, degrees of freedom, remember, is K minus 1.
So that'd be 3.
So it would be 3, right? Because I only have 4
Four
categories.
categories, right.
Gotta remember that it's the categories minus
Some
1.
categories.
Let's talk about where that is on our handout. Let's talk about where this is on our handout. On page 3, thank you, it's already there. Page 3. In the upper, that's my left,
Oh, goodness of fit.
upper left-hand corner, goodness of fit. You all up there on page 3? It talks about the observed, the expected. It tells you that K is the number of categories. N is the total number of trials, which also means the sample size. And it even tells you that degrees of freedom is K minus 1. So that's written there as well. And then they list chi-squared GOF. Or it says there's no calculator function.
What's
And you
that
could
mean, no calculator principle?
because in the old days, hardly anyone had this one, but the calculators were all old. So a lot of people had to do it by hand like I was showing you, and then just use the chi-squared CDF or the critical value. But you can either use this method or this method, or do it by hand, which I'm going to do this one by hand just to write it up. Then I'm going to use your calculators to save me some work.
So those are two different ones, the chi-square GOF test and then.
They're both the same test, but the problem is some calculators, the newer ones, have this built in. The older ones don't. So we have another one that we can load into yours. It runs as a program. So it's just not in there automatically. So you
Right.
can get this one in the math lab, but they do the same thing.
I did, but I still don't know what to put in.
For which one? This one or this one?
Good Fit 83.
This one. So it'll ask you, tell me what it asks you.
It just says program good FT83.
Now hit enter.
And then it says quit error.
Oh, that's the same thing that yours just said. Did you get a new one? Is it still saying quit error?
No.
Okay, so somebody corrupted some of our math lab calculators, so we just need to trade that one in for you. Let me borrow yours for a second, please.
It's under program.
So this one is under programs. And when you run it, I'm just going to start it here. With Good Fit 83, it shouldn't give you an error. The first thing it says is enter the number of outcomes. So in this case, there'd be 4 different outcomes, so you would enter the 4. And then all it does is it says observed values, and it gives you question marks. So you would just put in 59, enter, this enter, this enter. Then it'll say expected, and you type in your expecteds, and then it'll do everything for you. It's just that you have, I don't know if you got the same one she had, or if we have a couple of them.
I went and had them put it on my calculator.
Well, the one they just put on was corrupted. We need to figure out what's going on, because some of ours are working, and this is twice in one day already that that's not working. So we would need to double check that we download it from one that's working. You may have gotten it downloaded from a bad one, which is what happened. So we'll fix that after class. But these are supposed to do the same thing once we get the corrected program. And if you don't have either of those, thank you, Christiana, you can still do it by hand and use the chi-squared CDF, which I'm going to do for fun because I'm a total nerd. If I wanted to find my chi-squared here, the formula tells me to do what?
Observed minus expected.
Observed minus expected, so for the first category, it would be 59 minus 45
Squared
divided by 45 for that one.
Oh, and it would change with each.
Aha, it's gonna change for each one, which is why I wanted to write it out this time. Because the next one is,
See plus in there,
I'm sorry, what'd you say?
just talking out loud.
Oh, okay, that's
You
good.
plus each one.
Yeah, we add each one. 15 minus 15 divided by 15. Observed minus expected. The next one will be 2 minus 15. Divided by 15. So the expecteds are different here. So we can't just copy the same number like we were doing before. And then the very last one, 4 minus the 5. Divided by 5. And we can either spend quite a bit of time doing that calculation carefully, or someone who had chi-squared GOF or the working version of GoodFit 83 found what for this?
15.82.
15.82? Yeah? 15.82? That's my test statistic? Now what? Now we can find the critical value
With our chart.
using the chart and degrees of freedom.
Is that gonna change with each one?
Yes, degrees of freedom is always k minus 1. So our number of categories changes. In this case, we had 4 categories. So k minus 1 in this case is 4 minus 1. Last time we had 10 minus 1, so it does change based on that. That's my degrees of freedom. So what's my chi-squared star?
7.815.
7.815? So in terms of a picture, 0 happens to be the same as our first example, only because we had the same number of categories and the same significance level in that problem. The area in this tail right here is 0.05. Grab my red here. So if I'm using the critical value method, I'm going to do what?
Reject it.
Yeah, she says 15.82.
Is bigger than 7.
Where is it in this range over here? And it's definitely over here somewhere.
The critical.
In the critical region, yes. The critical region, which I also like to call the rejection region. So because 15.82 is in the critical region, in the rejection region, it tells me to
Reject.
reject H0. Let me label my steps here, I'm getting sloppy. This was step 1. This was step 2. I just worked on step 3. Here's my critical value. This is my chi-squared star, right? And my step 4 is to reject H0. What if I wanted to get my p-value and I had the old calculator? I know some of you have it in front of you. You're going to use it to check our work. How would I get the p-value with the old calculator?
X squared CDF.
Chi-squared CDF. And the p-value is from your test statistic and over. So it's this little tail, which is really sloppy all of a sudden. It's that little tail right there. So what would I put in the chi-squared CDF?
7.815.
Careful, I want the area that's red tail,
Oh, the red.
the red one, the one that goes with the test
So you
statistic.
have the 15.82.
Start with the 15.82.
Oh, the test
And
is
some
always goes in.
high
Yeah, the
number
test
and then-
statistic goes into your,
Goes
to get your p-value. Oops, I lost my degrees of freedom. Hang on.
Oh, 3.
Yep. Degrees of freedom 3 has to be in there. And what does your calculator tell you this equals? Those of you who are actually doing chi-squared CDF, what does it give you?
0.012.
012?
0, 0, sorry.
2 zeros?
0.001.
Those of you who used your goodness of fit test, did you get the same p-value? So the calculator's just doing all this work for us. We love our calculators. My p-value is less than 0.05. So again, we reject H0. Remember, you don't have to do both critical value and p-value. But when you're doing them online, as you've noticed, sometimes they ask for one, sometimes they ask for the other. Want to make sure you understand both. Step 5. Step 5 is to do what?
Conclude.
Conclusion. Do we have sufficient evidence or not?
Yes.
Oh, I heard yes and I heard no.
Well, because we rejected H.
Ah,
rejected
if you're
zero.
rejecting, you have evidence. That's like convicting someone, right? Convicting, you have evidence. Rejecting, you have evidence.
It is sufficient.
So there is, or we have sufficient evidence. To reject the claim. That, what were their words?
The observed frequencies agree with the proportions that are expected.
Yes, that the, thank you, the observed frequencies agree with expected proportions. So we rejected that they agreed with this claim up here, which is what it should have been based on genetics. I'm not a biology teacher. But what this tells me is that those fruit flies that they're looking at don't fit what it should have been. So maybe there's something different with these fruit flies. Maybe they've been exposed to something different. So there's something going on with these fruit flies to make this group not behave according to what it should be in terms of genetics, because we rejected that. Question. The subtle difference for the two types of problems in this section is sometimes the claim is that they're all equal, and sometimes the claim is like this one, where you have different percentages, and you have to calculate the number that goes into each. Let me tell you the biggest error, and hopefully you won't be the person who does it on the exam. A lot of times people will take the 56% of that, and the 18.75% of this number, and 18.75 of this number, and they'll get some expected values down here. How would they know that that is wrong?
Because it wouldn't equal the total.
It wouldn't add up to the total, it wouldn't add up to 80. Make sure your expected values still are the same 80 flies rearranged. Okay, let's move on to 11.2, which lucky for us has very little computation, and we all have the calculator function. Life will be easier at 11.2, but we get to learn something new with our calculator that we haven't seen yet.
Matrix.
A matrix, yes. You reading ahead?
Yeah. I kind of like woke up and I was like, oh no.
Where are we? Oops, I'm gonna do that now. 154, section 11.2. It's all about what's called contingency tables, which I like to call two-way tables. Both are listed here. This is for when you have two categorical variables and you're looking for a relationship. Maybe you're looking to see if there's a relationship between people who are in high school, junior high, or college, and whether or not, I don't know, they go to the movies once a month. And so either they do or they don't kind of thing. So those are yes or no questions about the movies, and then categories as well for what kind of school you go to. So you would make what's called a two-way table with categories going across, categories going down, and then we'll talk about the questions that go with it. So before I go and fill you in on the details, I just want to look at the example for the table they gave us, a little explanation of what's there. They were studying people that had what's called amalgam restorations. They're talking about fixing people's teeth. And so when you fix people's teeth, in example 4, you can either use amalgam or composite. So some dentist or whoever is trying to decide if one of them is better or worse for people. Are there more, adverse reactions for one versus the other? Are they equally, the same kind of percentages in terms of who has issues and who doesn't? So they have this table here where they took a bunch of people. Some had the amalgam restoration, some had composite. And then they counted in those two groups how many had adverse health conditions. I'm going to use my paraphrasing here. And how many were okay. That's not the word you have there. But if you don't have adverse reactions, you were okay. So they just counted. They said, okay, there were 135 people who had this kind of restoration, who had some kind of adverse health reaction. And there were 132 of them who had that kind of restoration that were okay. So we saw these tables before, like back when we did probability, just how many were in each kind of group. 145 had this type of restoration and had some kind of adverse health conditions, and 122 had that type and were okay. Now look at what the claim is, and then we'll go back up above. It says test for independence between the type of restoration and the presence of health conditions. What that means is, does one affect the other? If I said, hey, Mr. Dentist, how likely am I to have some adverse health condition? If he says, well, that depends. It depends on if you use amalgam or composite. If the answer depends on what type of restoration, then those would not be independent things. But if it doesn't matter, if they're independent, either type is not going to give me a higher or lower chance of having some kind of health condition. It'd be like if you said, hey, how likely am I going to get a raise? And I said, well, that depends on how often you've been late to work. So being late to work and getting a raise are not independent of each other. Where I wouldn't say, well, that depends on your favorite color. Your favorite color shouldn't affect whether or not you get a raise. So independent and dependent is there some relationship between the variables or not? Those are always the claims in this whole section. Are they independent or are they dependent? So now let's look up above where it tells you that. So we're doing what's called a test of independence. The HO will always be that the row and column variables are independent. And the H1 will be that they're dependent. Every time. So in this case, what is this variable measuring? What are we finding here in words? What do these represent? What are these?
Proportion.
Well, those are the
Categories.
proportions. But what are the categories of what? Are they favorite colors or favorite movies?
Material?
Material or type of restoration they called it. They're categorical always. But in this case, it's the type of restoration. Type of restoration. And what are these measuring? Health conditions. Whether or not you have adverse health conditions. Type of restoration and maybe chances of adverse conditions, health conditions. Are, I would maybe instead of chances, I'll put presence, are independent. I'm going to change one word here. Presence. I like that better, sounds better. presence. So let me underline a couple of things. First off, your H0 always has the independent in it, always. And then you're just describing this variable and that variable. So the one variable is the type of restoration, the other one is the presence of adverse health conditions, and we just say they're independent. And then guess what H1 is? That they're dependent. If you write it out once, I will not make you write it out the second time. As long as I know what they are. You need to describe the two variables. So either they're independent or they are dependent. Always going to be your two claims. From there, our calculator is going to do the rest of it. It's actually going to do a chi-squared test, but we need to enter our data into what's called a matrix. Let me turn the lights off and show you how to do this. Since we haven't seen this before, some of you are reading the directions on your notes and working ahead, which is great. Some of us need to see it. So the directions for this are the last piece of writing at the 2/3 of the way down the page, right underneath the HO and the H1. It says enter it into a matrix. I'll wait for this to get a little bit brighter. It's getting there. Can you guys see that? Getting there? So the matrix is kind of hidden. See down here where it says matrix in blue? Some of you have yellow on your calculator above the x to the -1 thing.
Yeah.
So to get that, because it's in blue or yellow and it's above this button, you have to hit the second button and then this one to get that. And it should look like this. Do we get to here? So that's the first thing, second x1. Then we need to choose edit, we need to create a matrix. So I'm going to move over to edit. And then there's all these names of these matrices, that's plural for matrix. So I'm just going to edit the first one. Some of you might have numbers here because somebody else already used your calculator and put some things in there. It's okay, we're just going to change them if you do have numbers. So I'm going to use matrix A, and I want to edit it, so I'm going to hit enter.
Is it clear to get all that out of there? Or?
No, just hit enter on matrix A. It'll change when we get in there.
Oh, okay.
Now you should be something like this. Mine says 1 by 1. Somebody else might have a 2 by 4.
Right.
So what size matrix do we have to fit our data here? How many rows and how many
2 by
columns?
2.
2 by 2. Important, it's always rows by columns. You could have a 2 by 3, which is different than a 3 by 2. Rows and then columns. Rows by columns. So I'm going to type over those numbers and change it to rows and columns. 2 by 2.
Columns go down.
Columns are, these are rows. These are rows, right? And these are columns. So 2 by 2. Oops. 2 by 2. So once I change it to 2 and 2, did you guys get yours changed?
Yeah.
You now should have a matrix here where you have 4 little numbers that you can type in. So I'm just going to type in my exact numbers that I have here.